You guys thinking Dirichlet processes? We could do that. Cool. I think I know how to motivate that and give you a 2-for-1. I like 2-for-1s.
What about just a little bit more on the theory behind the diff sample? Why it works?
Yeah.
Like Markov.
Okay. Yeah. Oh, those are contenders. Yeah. That's real enthusiasm. I do like that stuff. Dirichlet process implementation is a big gift sampler. So maybe we can slide both in. I don't know how well I can do. It's just like anything, there's a finite amount of time. I like the idea of maybe a day on more theory on gift sampling. Maybe Metropolis Hastings in general, and then gift sampling. We can kind of see that gift sampling, the acceptance rate is 1 if you're thinking about it in the Metropolis Hastings context and you're using the full conditional as the proposal. So we can see the immediate connection between those two algorithms. So a lot of people will show you more theory on MH and then say Gibbs is part of that. So collection. So I do like that. Show you more about stationary distributions, a little bit more Markov theory. That would be cool. It definitely connects. Let's have this discussion a little bit more on Friday and decide what we want to do next week. Today I'm going to show you everything you need to know, at least in theory, about homework 5, the regression problem. Let's just recap what we did last time. My battery ran out conveniently because there was a mistake on the board. I would have let that come through and made the correction in the slides like I normally do. I didn't have to do any of that because when I went to the video, I only had 29 minutes of video. This is a product of spring break, and I used lithium batteries, and I left my camera on. So when I went to charge it or look at how much was in there, it told me 33%. But lithium, if you know anything about it, it's not reliable when you leave it out in the cold. So in my office got kind of cold, I guess over the break. That's all true. So my motorcycles are the same way. Some of my motorcycles are run with alkaline batteries just because of this. So anyway, sorry about that. Let's just recap the way we should have concluded last time. So this is the Bayes factor we worked out. Let me remind you what the problem is. We're studying this problem. So xi's are coming from a normal distribution with mean theta, variance sigma squared. Everything's IID, so standard setup. I goes from 1 to n. So we can write down a likelihood model from all of this. I'm going to end up putting down a null hypothesis. I want to test theta is equal to theta naught versus this alternative. Theta is something different from theta naught. We have wrapped on this, and if you've taken my inference class, I've wrapped on it for a year now. This is a crazy question. It's not well posed. It's not well stated what you even mean. Is theta theta naught? Probably not. So the audacity that you would have picked the right theta naught. It's even worse than this. So in real data land, this probably isn't true. It might be approximately true or something like that. So there are repercussions to that as well. So if you're asking this question, can I measure a measurable difference saying that it's not theta naught? Probably the answer is yes. You can collect a lot of data in a real problem to say it's not actually theta naught. It's probably something different. I would suggest thinking about it that way. That you need to think about the problem is how far from theta naught would you need to be before you reject it? How far would you need to be before there's a meaningful difference? So, and that is a subjective question, and it just is. It depends on the context of the problem. So, non-Bayesians omit that sort of thinking, and they just say, can I measure the difference and show that it's just not? You know, and kind of calibrate error rates on it. there is a presumption in there that the data was actually distributed that way. And so if you reject, you might be rejecting that and not actually the hypothesis. So I'd say there's all these assumptions baked in. If this is all true, then you can use it, to test theta naught. And maybe if you were a physicist and you had absolute control over your experiment, and you knew everything, and you had all this control on you, you spent bazillions and trillions of dollars, like CERN or something like that. They want to know, does this little tiny particle exist? So they're going to get their machine calibrated. They're going to sit there and repeat the exercise over and over again. They're going to have frequentist control over everything. They're going to be able to say, how far do I need to drive down the precision of this experiment, i.e. what the meaningful difference is, because I know what machine precision is on this. So I'm going to need to drive our precision down farther, which is a sample size calculation. It's really a power calculation. So if you did all of that, and you had that kind of control, I would say the Neyman-Pearsonian setup is meaningful. So saying that, in a lot of cases, you could also treat that as being a Bayesian. And we could write down some priors. So I could say our prior on the null space is the delta function. Just the indicator, if you like to think about it that way. If you're thinking about a density, it's infinitely high and it's got no width. Once you integrate over it, it's just a 1 or a 0. And I can calibrate the alternative hypothesis. And so I might be thinking, I'm going to make this normal, centered at theta naught, otherwise why would I be testing theta naught? And I can introduce this variance parameter. And this is really gauging how far from the null would we need to be in a probabilistic sense before we rejected it. I think all the importance in a Bayesian hypothesis test is on that question, on that. You're going to form a Bayes factor using these two different prior distributions. And it's basically, that Bayes factor is just a comparison between two different ideas. Being farther away from theta naught or being theta naught. It's comparing that in a ratio sense, which is the right thing to do. It's the more powerful thing to do. If you just think about Neyman-Pearson, it's telling you to work in ratios. So the Bayes factor kind of makes sense. So if you want to draw on some theory you might have known earlier, you can say, yeah, that makes sense instead of dealing with differences. So when likelihoods come up, they should always come in ratios. So this is an important question, and you always have to deal with it. Now, I would agree, it's not unreasonable to say, look, I standardized my data, and I just picked that to be 1. And I'm thinking of, maybe I'm just thinking if it's like far away in that standardized sense. It's kind of a cop-out, but in some cases, you just don't know what to do. So I would say if you cannot think about this in the context of your problem, you don't know anything about your problem. That's an easy thing for me to say standing up here at the board. So I don't know anything about your problem either. So I just know that we're all working on stuff, and you should be able to think about this. What is a meaningful difference? Even if you're following the Neyman-Pearsonian thing, you should calibrate that and do the power calculation up front. If you're just collecting n because that's what you got, and you're computing a p-value, I would say huge violation, but it's the same violation everybody's been making, and it's the most embarrassing thing in all of statistics. It's just true. So everybody knows it, and if you don't know it, now you do. So what are you going to do about it? Most of the time, I just want to avoid this question. I'll tell you what theta is. In some cases, you just have this super high dimensional space, and you don't really know, and you can't be thinking about every single theta in that space. So I understand there's limitations to that idea. I would say this general problem in 1D, is probably the major culprit. Why are we even talking about this? But in high D, I understand that you got to do something. Okay. Anyway, I would say this is the big question mark. how far from the null do you need to be, and you have to understand how your data is collected and the variability in your data, what you expect to see, and if you don't like thinking that way, you're not a statistician. That is exactly what statisticians think about. So what is responsible for the variability in their data and what's meaningful? So I don't think that's an automatic sort of thing. And that's what makes this so hard. And I'll read you an excerpt from Jim Berger's book. And Jim has an interesting story. So he was an ardent frequentist. So went to get his PhD, became a frequentist, didn't know much about Bayes, so was doing basic frequentist type inference, MLEs, things like that. They're not bad. So they can be really good. They can suffer in some cases. And then he started studying decision theory. And so what are the properties of decision theory and what are the guarantees on everything? And he changed his mind. So he wrote this book a long time ago, Bayesian Decision Theory. He's written several other books. And so, and I would say that, you know, he's kind of one of our friendly forefathers of statistics that, you know, can say things in eloquent ways and not make a lot of enemies. And I think that that was helpful as well. So we still use all this p-value stuff. I want to say something about that in a moment. Okay, just in terms of this basic problem, we worked out the Bayes factor. There was a mistake there last time, and we showed that as psi squared went to infinity, this part right here converges to 1. So it's just whatever this thing is. So this whole piece is converging to e to the minus half z squared, which is just the likelihood ratio test stat. I just want to point out that is the likelihood ratio test stat. So this part right here is the likelihood ratio test statistic. So it's the maximizations over both likelihoods over those two different hypothesis sets. So maximize it over theta naught, maximize, then marginalize over the alternative hypothesis. Or maximize it over the alternative hypothesis. Let me write that down. So this is just the max over h naught. So that just means theta is equal to theta naught. That's a very easy maximization to work on in terms. And I'm going to maximize over the entire space. You'll forgive me for removing theta naught. I assure you. If I remove that one point, it won't change anything. This is what we learned in calculus. So I'm just going to put that same point back in there. It doesn't change the answer to all of this. This is going to look like, you'll forgive me for getting rid of my normalizing constants, the root 2 pi's. They show up in both the denominator and the numerator. This is e to the minus 1/2 x bar minus theta naught squared over sigma squared. This is e to the minus 1/2 x bar. Where does this maximize at? Oh, divided by n, divided by n. Where does this maximize at? What's the maximum likelihood estimator for a normal distribution for the mean? X bar, yeah, it is. That's a pretty easy calculation to run through. That's 1. Is that. So that is kind of what you're doing is you're altering in some sense through this integration step and averaging over everything. You're changing kind of the dynamics of the problem. You're changing it through the alternative variance and through n as well. So now we're thinking about what z means, but we're also asking the question, what was n? So let me just bring up this point. I've said this before in the past. Let me try to drive it home. If I had let's say I had 2 experimenters that are doing 2 different experiments. They have different ways of doing their experiments, but they're both measuring theta, same theta. They're thinking of theta the same way. It means the same thing to them. One experimenter has a p-value of 0.04. Let's make it 0.049 so it's even more interesting. The other experimenter coincidentally has a p-value of 0.049 as well. So they both compute 0.049. There's more to the story. Experimenter 1 did this with 100 data points. Everything's normally distributed. I could have said 31. I could have said 5. And then all the same properties, no worries there if everything was normally distributed. If it wasn't normally distributed, we might be concerned about the CLT. So let's remove ourselves from that. Everything's normal. Second experimenter has a p-value of 0.049, and they have 1 billion data points. Who has more evidence against the null? Experimenter 1 that used 100 data points, or experimenter 2 that used 1 billion? Serby. 2. So Serby says 2. They used 1 billion. That's better. So they've got a p-value of 0.049. Yeah, right. So I would say, so experimenter 2 used 1 billion data points. Anybody want to argue the other way?
I don't know if exactly what I'm arguing right, but probably the billion is like an infinitesimally small.
Right.
So yeah, I'd probably run it off, not arguing the other way. Because if you collected more, the p-value would probably go down because the effect size is larger.
Let's just think about what Z is. So they both have the same Z-score because they have the same p-value. So x bar n minus theta naught, absolute value, over sigma over root n. Now these have different experimenters right here, so I'll make this experimenter 1 and experimenter 2, and I'll just put an I on there, just to indicate we've got 2 different data sets, 2 different n's in there. If this was 1 billion right here, this number way down here is much, much smaller. So what does that mean about that? Let me think about it this way. If I thought about just the p-values, these are kind of like your homework. Your homework, what you were doing, I have 0.049. Experimenter 2, this is 1 bill. It took them that long to get this thing. There is some difference, it appears. It took them forever to get there. And experimenter 1, in 100 data points, bam, they came way down there super quick. And that p-value, if they collected 1 billion data points, would be way smaller. So they're right on top of the goal. Or that effect size is bigger. So it's what? So they're farther away. So I would say it's the other way around. If you use less data points to get there, then that's a statement about how big that difference is between x bar and theta naught. Let's think about this, just in terms of the limit again. So let's just get rid of this and think again. If this thing was 1.96, that's not 0.049, that's the 0.05 level. So if you want to subtract off epsilon or add epsilon, I don't care the way you think about this. If I do this and I say this happened in the limit is n went to infinity, again, this is a conceptual exercise. What would that mean? It would mean that this is tiny right here. This is like as small as you can get. So what does that mean about this? This is also tiny, but it came down to tiny at rate 1.96 compared to what the denominator was doing. And so that means that this is tiny. So what this means, if this actually converged, because we know that goes to 0, this has to go to 0 as well. So what that means is x bar n is converging to theta, but for this to be tiny, this has to be equal to theta naught. So theta is equal to theta naught. So I would say if n is huge and p is 0.05, my argument would be theta is not theta naught, because it should be smaller. Does that make sense? So the p-value should have been smaller. It's only 0.05 and you had 1 billion data points? Jeez. So I always ask that question. You did a sharp test, so, and a lot of people get suckered right into this. I used a lot of data. Well, then it doesn't mean anything. So if you had like, if this happened in like 7 data points, that's a different thing. That must mean that, you know, these are really far apart from each other. So just think about that a little bit.
So if the p-value actually represented essentially the probability of theta not being equal to theta naught,
It's not.
if it actually did represent that, you would think it wouldn't depend on the number of data points.
If it did represent that, I would call you a Bayesian and say you must have come up with a posterior probability of that thing. It doesn't, and that's the big misconception, is that people like to think about it that way and it just has nothing to do with it, especially in the sharp case. So it really is a p-duct alpha, and if you pre-specified alpha and you picked n for a good reason, and it's meaningful. It's what they would have taught you a long time ago, but people started collecting a lot of data. And they said, well, I guess go do whatever you want with all this stuff. Repercussion is the error rates are through the roof. Just go get more data until you reject your null so you can write your paper. So it's a big problem. How big of a problem, I don't know. So gives me a job. So gives me something to talk about. Anyway, I would say the scientist with a small p-value with lower amount of data has way more information against the null. So that if you had a ton of data, I would expect that p-value to be really small if the null wasn't true. It's really a question of how far away from the truth was it is going to determine that rate of how fast the p-value cascades. And that's the question. Let's think about this. So here's this Bayes factor that we get, has something to do with likelihood ratio. Point is this thing was converging to 0 as psi squared went to infinity. This thing right here goes off to infinity as psi squared goes to infinity. So the Bayes factor goes off to infinity as I use the flat prior, and I use it in the non-heuristic way. I actually take the limit and don't just plug in a constant, an arbitrary constant. So that constant won't cancel, so you have no business doing that. My interpretation of that is you need to be infinitely far from the null before you reject the null, no problems for me. So I like that interpretation. I just understand what a Bayes factor is doing. It's setting up a comparison. If you didn't pick that comparator in a meaningful way, forget your analysis. So I always think in statistics, it's all about the way you compare and what you compare to and how you compare it. And that's how you build meaning into things. That's not math. That's not robots. That's decision making. And so I like going slow when I do this sort of stuff. Think about what the repercussions are. Meaningful differences. Compared to what? I think you can't get away from that if we let the robots decide compared to what. They're going to optimize something crazy for us. Something we didn't anticipate. So hopefully we can still have a little bit of control of our comparator. I do think this isn't the best prior to use. It's convenient. I can do the math. You might use other sorts of priors, and there's been a lot of debate about that. Asymptotically, I think this works out. So I think it's better than the typical p-value and just using a p-value because we haven't really considered what the effect size is, and we haven't considered n properly. Okay, let me read Jim's comment about this. So what he's saying is, if you use the flat prior, you get a nonsensical answer. So Jim says, the conflict in the above example, this thing, is of such interest that it deserves further investigation. The Bayesian analysis can of course be questioned because of the choice of prior. The assumption of a normal form can be shown to have no real bearing on the issue unless x bar minus theta naught is large. I disagree, but he has some limits to that thinking, and my limits are outside of his bounds. So I think it matters that it's, you know, if it were T4, it would make a difference. So a little bit of a difference. It depends on the departure. But what he's saying is this comment I said before, so I'll contradict myself, is that if the model is misspecified, there is a balancing act between the numerator and the denominator that you don't really see when you compute a p-value. Because you're just using one of the models and you're using the alternative to direct the tail direction, is the way that ends up getting used. And the choices of theta naught centering the prior and pi naught being a half are natural. So, okay, so half probability on each thing. So what they're saying, when they compute the posterior probability, they take the Bayes factor, let me do this thing. Bayes factor inverse, it's just Bayes' theorem in disguise, and they compute that Bayes factor and they roll it over to a posterior probability. So that's the pi naught that they're talking about. I don't have any great problem with using a half in this problem. I don't think that's the big deal. Indeed, if one were trying to be objective, these choices would seem to virtually be mandatory. I think that's probably true. So I can't argue with that too hard. One could certainly question the choice of the variance. So in some of these calculations, when we did this thing right here, I picked psi squared to be equal to sigma squared to do this calculation down here that we talked about last time. So, and I'm going to talk about this bound on the posterior probability in just a moment. Let's just finish reading this, but they're basically talking about these results that we were pointing at last time. One could certainly question these choices. However, Jeffries argues that such a choice is in objective testing, but the answer could definitely depend crucially on the choice for that prior variance. He has different notation. Jeffries actually prefers a Cauchy form for the prior, but again, the form matters only in extreme cases. I think Jeffries is right. So I love changing this to a Cauchy. Problem is it's not conjugate anymore. But we already know the trick for all of that. So I use normal, and then I integrate over the variance, and I can turn it into Cauchy in my Gibbs sampler just by integrating over that variance. So I can use the conjugate forms and have nice stuff to compute with, but I would agree analytically we can't write down the solution. So I almost mandatorily, when I do these sort of problems, and I like squirm when I'm forced into this situation. I don't want to do it. You know, I want to do a different problem. But if I'm forced into it, I choose Cauchy. I've done it probably about a dozen times. I always use Cauchy tails. So I actually use something that's different from Cauchy, that's even messier on the chalkboard, but I insist on the fat tails. So that would come up maybe in an advanced Bayes class. So I just want to point out, this is that result that we're seeing, what happens to the posterior probability. So this is the probability of H naught given X bar in all of this. So these are these probabilities as n increases, and this is for different corresponding z's. The p-values are clear what they are right here. This is 0.05, this is 0.1. So what we see is these posterior probabilities getting higher and higher and higher is the sample size increases. So for 1.96 with a corresponding p-value of 0.05, for this problem, we notice that the posterior probability is climbing and climbing asymptotically. There's some weird stuff going on with one data point. The prior kind of pulls this in the wrong direction for a second. So not long. You don't need much data to overcome that behavior. And this just starts climbing up and up and up. So this was my basic argument that if n was huge, I would think theta was theta naught in the limit. If you got that 1.96 for very, very, very large n, what it means is X bar is right on top of theta naught. So that's that same behavior right there. So it kind of makes sense. So if you buy into that's what it should mean, and it's not just about that standard error, because that could be epsilon. And so that's the difference between practical significance and statistical significance. I'll take practical significance, thank you very much. So, and I think the Bayesian gives you that. I think if you did the full power thing with Neyman Pearson, you in some way are getting something like that. You've at least considered that effect size and what n should be. The Bayesian bakes that all into one number, and that's what it is. I want to point out also, there was a commission, and I posted 2 papers on the website. You can look at them if you want. They're basically discussion papers on the abuses of using p-values. And it stems from this very problem, and there were 2 committees that were populated. There was a frequentist committee, and there was a Bayesian committee, and they were supposed to write papers. I didn't give you the full-blown papers on that. I gave you what spurred the debate, and I gave you the summary paper, where they baked in what everybody said in committee. Now this, if you've ever been on a committee, nothing good happens. So the Bayesian said, if you're going to use a p-value, do not use the 1.96 limit. Don't use the 0.5 limit. That's not enough. So what they've done is basically constructed this table. There's more values I could put into this, but there's a bound on the p-value regardless of which size squared I pick, just as long as it's finite. And that bound on the posterior probability, that's what I meant to say, bound on the posterior probability are these numbers. So 1.27, so for a 1.96 z-score that has a corresponding p-value of 0.05, the bound on the posterior probability is about 13%. So it's saying there's at least a 13% chance that that's true. And so 0.05 is just not strong evidence. So the Bayesians said if you're going to use p-value, put it at the 0.1 level. And this was the only thing they could agree on what to do. So, but it at least puts that bound on, which is smaller. I was mad that, what? Proceed as you are, you know, but just do this. Oh, come on, man. So that's a horrible prescription. You got to think more about the problem, but that's where it's hard to get people to agree. So I actually like the frequentist recommendations better. They said if you're going to do Neyman Pearson, make sure you do it right. Then do the effect size calibration. You shouldn't be using p-values in all these observational settings. We never intended that. We just teach it. So that sort of thing. That's also in the papers. Cobb is cited as saying we teach it because people use it, and people use it because we teach it.
What do you mean by observational?
I just come in and I just grab a whole bunch of data. So a well-designed experiment is where I've controlled the groups, the strata, I've controlled the sample size. Observational data is, I just see it, you know, go collect it all. What does it all mean? So n was given to you just by whatever. So if you scrape the internet for data or something like that, that would be an observational study. So you're not prospectively, you know, collecting the data. You don't have control over the whole process. Just getting it, and then you throw down some model assumptions on it, and you've got n. So they're saying don't compute p-values in those cases, especially with all this stuff on the internet. You know, because your n is huge. So you're going to get p-values that are small, guaranteed. You know, everybody's thrilled about that, right? So I would say if you don't want to do science, either do that or treat this problem and be a Bayesian and just use that as a prior. And don't forget about that part. If you integrate over a point, you'll get a posterior probability of 0 every single time. Data-free, assumption-free. You want small, the Bayesian can give you small by being even more nonsensical and not hiding what they're doing. Nobody would ever do that. It's meant to be a joke, but if you want to do things that aren't scientific, there's plenty of ways you can exploit statistics. And the exploitation of Neyman Pearson has been one of the paramount culprits. Let me just talk about that bound real quick again. All I've done is I've taken the likelihood ratio test right here and I substituted it for the Bayes factor in this. That's all that happens. And it creates a bound that is at least as big That bound goes in one direction. Let's just look at this. What I've done in the denominator, am I not erased today? What I've done in the denominator of the base factor this is going to be 1 over root, I'll get rid of these, we don't need those. E to the minus 1/2 x bar minus theta naught squared over sigma squared over n. And this one is going to be integral of e to the minus, I'm going to write it like this, likelihood theta x bar pi h1 theta d theta. This is proper. If we use the improper prior, we're going to get a crazy answer. If you take the limit, this thing will explode to infinity. If you just substitute a c in there, you're choosing a c, you'll get an arbitrary number. So both are not wise. So what I'm going to do with this thing is I'm going to bound this by the max likelihood pi h1 theta d theta. So that's the max likelihood. I've already gotten rid of my root 2 pi's. I can't put them in the numerator and the denominator. I need to encode the likelihood exactly the same way. So I'm going to not put in my root 2 pi's in here. But this thing right here, the max likelihood ratio test stat, or sorry, just the max likelihood is e to the minus 1/2 x bar minus x bar. It maximizes at x bar. You don't believe me? Pick a log, take a derivative, basic calculus problem. So that's just that right there. So I bounded that by this thing, and I've substituted in, what did I actually compute? I computed the likelihood ratio test stat. So I have a bound in that direction, and I'll let you do the acrobatic mental gymnastics and convince yourself that the bound implies that that thing is bigger than that. Keep in mind, you've got to flip it over here. So you think about it in terms of what this whole ratio is doing, flip that thing upside down, and then flip that thing upside down again. So anyway, it does go bigger, so it's not guaranteed to be smaller. That would have been a nice thing. So it actually goes the other direction. So that's the disagreement. So I think you got to do something. I don't know how to pick psi in general. I don't know how to teach a class on that. That would be in your home department unless you're in statistics. And I'm just going to say you have to go talk to your collaborators about it. And that is hard. So, but that is what I think is meaningful science, is that conversation that you end up having. And if you can't come to conclusions on it, well, you can only say so much. What are you going to end up doing? Probably standardize your data and pick that thing to be 1. That thing being the alternative variance. Any questions about that? Gross disagreement between posterior probabilities and p-values. So C is 1.96. What can the posterior probability be? Anything. Almost. There's a bound, you know? So anything, almost. Big numbers. So big disagreement. Somebody says p-value 0.05, and a Bayesian says, but the posterior probability is 0.99. So what gives? So what do you think it is? Either you've picked a really crazy alternative variance, or n is really high. It's one of those two things. I give you a conversation to have. So I think that's actually good practice. I don't know if people talk to each other anymore, but I think they should. And this is something to talk about. Okay, let's study a slightly different problem. Same problem in disguise. Y eyes. So new example. example. This is really homework 5. So it's a regression problem. I'll talk about the encoding of all of this. I'll say this P goes from 1 to cap P, the dimensionality of the problem. I've got some XI's in here, XIP, and I've got some beta P's. Plus some errors. So we'll make this real easy. This is normal sigma squared. So this is standard regression. So just fitting some stuff. Now I want to just be real clear about my notation that I've used on the homework. I can't exactly get the notation to be general to wrap around every problem. But if I give you a matrix of a bunch of x's, there might be interaction terms where, you know, one of the x's gets multiplied by another x in the thing, and that's an interaction that two things might covary together, and you want to capture that. So it's not just marginal effects. So in the data set that I've given you a bunch of x's, and there might be two-way interactions. There's not three-way interactions, but you'll have to think through that model space and how to use those x's. Also, the way I've encoded this on the board doesn't necessarily imply that one of these is an intercept. So maybe the first term here is a 1 right here. So if you wanted an intercept, you're going to have to put it in. In the data set that I've provided you online, I didn't put in the column of 1s. I want you to play around with those. There's not three-way interactions. There's not four-way interactions. There's some two-way interactions. And there's no intercept encoded in that matrix. So you'll have to come up with the design matrix yourself. You know, you'll have to come up with the formatting of that matrix and do some exploratory investigations. If you do not put an intercept into the model, I guarantee you'll get crazy answers. You're going to need the intercept. I didn't put it in there for you. You might want to check for multicollinearity in things. It's possible that I put something in there that's collinear, so I took a column and multiplied it by some factor, or I took a linear combination and I put it in there. For one of the data sets, I did it. So one of the columns, or a couple of the columns, are linear combinations of other columns, and if you don't yank them out, you'll get kind of arbitrary answers. And I'll be able to spot it. So which stuff do you take out? You tell me. It's kind of arbitrary. So all that Stat 101 stuff, I assume you've all fit a regression model and people have talked to you about these issues. So this basic problem, and we might ask these questions. H naught is beta j, where j is an element of 1 to p, cap p, equal to 0. So I might do that. I might want to work out a Bayes factor for this sort of thing. And I might want to work out some full conditionals for these. And what you can do is you can take these full conditionals and drop them into a Gibbs sampler and figure out the overall joint space of which beta j's are 0. So you can deal with this problem for each one of the beta j's and kind of try to figure out which ones are in the model and which ones aren't. Now, of course, if you remove 1, you might want to put 1 back and something like that. So if you're doing them one by one, you're going to need to invoke an iterative scheme. And so Gibbs sampling comes to mind for that. And I'm going to tell you next time how to make the Gibbs sampler. What I'd like you to do is stare over the notes that I presented for you, and we'll go over these next time. So we're going to work through the Bayes factor for this problem. So what does the Bayesian do? Compute the Bayes factor, work out the posterior probability. If I had the posterior probability, what would I do next in a Gibbs sampling sense? I'd flip a coin with that probability and decide whether or not I wanted to remove that beta or leave it in. And it's that simple. Flip the coin with that probability. So in or out. Now it's a probabilistic thing, so I'm going to want to mix over that and integrate over that idea. That's what Gibbs samplers do for you. Auto integration. There we go. The Bayes factor for this calculation, I want you to just stare at this. This beta j is equal to 0 versus beta j not equal to 0 and my Bayes factors are going to be unconditional on all the other betas. What does that mean? So I'm not conditioning on all the betas. How did I get rid of them? Huh? That's it. I averaged them all out. So all the other betas I'm just averaging out. So I'm going to create an algorithm with this idea that's just telling us the inclusion or exclusion. If you want to know what the betas are, at the end of the iteration, you can sample that beta if you would like to. So, or you could figure out which model you believe are best, and then you can just figure out what the joint betas are for those models. So I'm going to teach you how to do this in a computationally efficient way where you're not carrying all the betas with you and slowing down the convergence of the algorithm. So this is beta j is equal to 0 versus the beta j is not equal to 0, where all the other beta j's, all the other betas not j, are integrated out. I give you some notation that you can follow. So I give you these matrices x to the minus j. What is x to the minus j? It's just like x where I drop the jth column. So that's my notation right there. We'll come back to this next time. And so basically I can format a few expectations and variances. So the expectation is a vector, and the variances are going to be matrices. And these should look familiar to you. And so actually the ridge estimates, if you know what that is. We'll talk about that as well. So once I drop the columns, I can do something very similarly and compute some x transpose x inverse stuff with a penalty plugged in there. That's actually coming from the alternative prior, is this. And that's the same penalty you get from ridge regression. So, or Tigranov regularization, depending on which camp you come from. So the Bayes factor for this problem is written down right here. That's it. It's the ratio of two things. There is some cancellation in like the size, but I left them in there just so you could see everything. The numerator is worked out here. We'll go through this next time. The denominator is worked out here. And the Bayes factor is there, the thing that we had on the first page. I'm going to be walking through this a little bit more slowly next time. But I'm going to give you a chance to kind of see it in just slightly different writing. I worked this out twice to make sure I had it right. I didn't copy it down from a book. Make sure I can still do this. And I've got the numerator right here, same calculation. And I've got the denominator on that. So I put in some extra annotation in here. We can look at this next time. We'll walk through both of them, make sure there's no errors. But basically, what are you encoding? You're encoding this Bayes factor, and then you're computing the probability out of it. So, and that's all you're doing. If you want to play around with a pi notch, you could. So, and see how that impacts things in your Gibbs sampler. But you're going to compute this into probabilities, and you're just coin flipping with the corresponding probabilities in your Gibbs sampler. So I prepared a handout. I photocopied the last page front and back. And so you guys are more than welcome to look over this and study it before next time, and we'll kind of go through that. And then we'll make an agreement as to what we want to do next week. So whether it's Dirichlet processes or more theory on Metropolis Hastings, of course we could stick around all through Christmas break, and I'd be willing to do it. So, and we can go through it and extend it all. I'll tell you what. As an experiment, I'll say if you would like to meet on Christmas, I'm open to it. I'm just curious what will happen. My wife is going to kill me. So we should have a pretty gentle landing to the whole semester. Okay, we'll do a review tomorrow. Did I already do that? We'll do a review tomorrow at 6 o'clock. So if you guys are up for it, I'll see you then. Otherwise, I'll see you on Friday.